As we alluded to at the end of the last section, in this section, we're going to look at graphing equations described in polar coordinates in the xy plane. So example one, we've actually talked about these at the end of the last section. We're asked to graph the following polar equations in the xy plane. Here, in example one, we're graphing constant values for r and theta. Okay, so what does it mean to graph an equation? Right? To graph an equation, we want to graph all points r theta that make the equation true. All right. So in this particular case, we're specifying that r equals 4. So we're graphing all points of the form 4 comma theta. Now we know that r equals 4 means that we're going to be 4 units out from the origin here. And as we move theta around, that's going to sweep out a circle centered at the origin of radius 4. So we can just pretend that's a circle. Okay. Over here, r equals negative 3 square root of 2. So we'd be graphing all points of the form negative 3 square root of 2 comma theta. Now the negative here just tells us that when we start, instead of moving to the right of the origin and then rotating around a circle of radius 3 root 2, we're going to be moving to the left. We can approximate 3 square root 2. Square root 2 is going to be roughly 1.4-ish or 1.5-ish. So you multiply that by 3, right? That'd be, right, 3 plus 1.5, like 4.5. Okay. So you can label these sort of however you want. So if you want to label this as, well, I guess 4.5, 1, 2, 3, 4.5, right? So starting here and letting theta be whatever it wants would still graph out a circle of radius 3 square root of 2 centered at the origin. Okay. The fact that theta isn't represented at all in these two equations, we would describe theta as a free variable. Okay, meaning it's free to be whatever it wants. All right, moving on. Here's some equations that fix theta. There's no r to be seen, so r is free to be whatever it wants to be. So let's look at theta equals 5 pi over 4. So theta equals 5 pi over 4 just specifies how far we're rotating from the positive x-axis. So 5 pi over 4 would land you right down there. So that would be theta is 5 pi over 4. And r is free. So if r is 0, then we're just sitting and spinning there at the origin. If r is positive, then we'd be heading out this way. If r is negative, we would be heading back this way. And so this is going to sweep out this line through the origin. So that's your theta equals 5 pi over 4. Once again, we're looking at all points r comma 5 pi over 4. Theta equals negative 3 pi over 2, same kind of thing. We're specifying the rotation here. Negative 3 pi over 4 means we start from the positive x-axis and rotate clockwise, 3 pi over 2. So that would be getting us set up along the positive y-axis. Once again, if we have a positive, or if we have a 0 r value, that we would be stuck at the origin. A positive r value would have us be sweeping up the positive y-axis. A negative r value would have us sweeping down. So this is just another way to describe the y-axis. So theta equals negative 3 pi over 2. Once again, we're looking at all values, all points r, of the form r comma negative 3 pi over 2. Okay? So constant r's and thetas. If you have an equation of the form r equals a, you're looking at a circle centered at the origin with radius absolute value a. So like we had here, the negative just tells us how we start from the origin, but we capture the entire circle by rotating around. Theta equals alpha. Constant theta is a line containing the terminal side of alpha. All right. go. Okay. So now we're going to talk about more complicated equations, and this is where things can get a little dicey. Let's look at the equation r equals 6 cosine theta. So one way we could start by graphing is what we always do, is just start plugging in values of theta, figuring out values of r, and then plotting those points in the plane. So remember, these are polar coordinates. All right. So I plug in 0, get out 6. The polar coordinate 6, 0 means I start here at the origin. I move out 6 along the positive x-axis, and then I don't rotate at all. So this would be the first point here. So if I want to label these points just to kind of show you what's going on. So that's point 1. Then at pi over 4, I get 3 root 2. So I'd go out 3 root 2 and rotate pi over 4. That's point 2. Point 3, when I plug in pi over 2, r is 0, which means I'm back at the origin. So that's point 3. Point 4 is negative 3 square root of 2, comma 3 pi over 4. So I would move out to the left along the negative x-axis and rotate 3 pi over 4. That would get me to point 4. Pi, I get negative 6. So negative 6 pi means I go out negative 6 and rotate pi. I'm back here at the first point. And as I go around, you see what's happening is I'm just repeating these points. So this gives us 4 points. All right. Now you can try to connect those with a pleasing fashion, right? And maybe see that, you know, you would sweep out this circle here. But what I'm trying to motivate here is, instead of looking at just some specific points, because of how polar coordinates work, you'll often get back to the same place, and you're not really getting enough information to draw a reasonable graph. So here's how I like to do this. We know how to graph these kinds of things, like what, thinking back to was it section 10.3, where like if we had y equals 6 cosine of t, we know how to graph this. All right, that's your standard cosine curve. It's got the same frequency as normal. There's no phase shift. There's no baseline shift. We just have an amplitude of 6. So let's graph this in the r theta plane. So notice the labels here. This is in the r theta plane. This shows how r and theta connect. So between 0 and pi over 2, r goes from 6 and gradually decreases to 3. So remember, these cosine curves are smooth and continuous, so gradually decreases. So what does that look like in the xy plane now? Theta equals 0 is the positive x-axis. Theta equals pi over 2 is running up to the positive y-axis. So theta going from 0 to pi over 2 here on the left corresponds to this rotation on the right. I start out 6 units away from the origin, and then r drops to 0. R equals 0 is the origin. So I start out at 6, and as I rotate from 0 to pi over 2, I'm coming back into the origin. Okay? So this arc corresponds to this arc. Now let's go through the second arc. From pi over 2 to pi, the r values become negative. So here's the pi over 2 and pi. So as theta rotates here, the r values are negative. They go from 0 to negative 6. So instead of plotting here, since the r's are negative, remember they're pi units off, so they're being graphed in the opposite quadrant. So instead of graphing in quadrant 2, I'm graphing in quadrant 4. So notice I pick up where I left off, and I'm going to sweep to 6 units away from the origin. So I start at the origin, that's r equals 0, and r equals negative 6. That just means I'm 6 units away, but in the opposite direction. So I'm back to here. All right. Now, if I keep going, look what happens. All right, so one cycle here gives me one cycle here. And if I were to keep going, from, say, pi to 3 pi over 2, if I were to keep going, look what would happen. So pi to 3 pi over 2 would be sweeping angles here, but these r values are still negative. So the r starts at -6, which means I'm starting here, and I'd be retracing. And then the same thing here, I'd be retracing these values, okay? So even though the frequency of this cosine is 1, I sweep out the entire graph in the xy plane in half the time, right? Instead of going from 0 to 2 pi, it's just 0 to pi, and that sweeps it out just once, okay? So that's how I like to go through these. I mentioned that Desmos, I think last time we mentioned Desmos can handle this. You can actually have your grid look like x and y or r and theta. So there's your polar graph, and you can actually do this here. R equals 6 cosine theta. And that'll check your graph, okay? It defaults, it'll give you some default. All right, here's 0 to pi, traces it out. But if you wanted to, you can add a slider. So 0 to a, and let's have a go from 0 to 2 pi with like a step of, I don't know, pi over 6 or something. Or, all right. So you can actually see it sweep out here. So a equals 0, and then you can see it as you're tracing around here. Okay. Or you could make that a sort of a continuous slider and just don't have the step in at all. And then you can see it, whoops, here we go. Then you can see it sweep things out, right? But if you want to make sure you're sweeping out the right arc with the right arc, I think we had arcs every pi over 2. So there's 0. Oh, I'm sorry. I have the wrong thing. So I want to go 0 to, say, 2 pi with the step of pi over 2. Then there's 0 to pi over 2 is the first chunk, and then pi over 2 to pi is second chunk, and you can see we've swept the whole thing out again. Okay, so this is a nice tool in Desmos because it helps you figure out not only if you're getting the right shape, but if you're drawing the right pieces in the right places. All right, so this will be really helpful as you move through here. So let's take a look at example 2. R equals 4 minus 2 sine of theta. So once again, my advice is we start graphing. We graph this in the r theta plane first. So we graph this over here with the r theta plane. And so thinking back to section 10.3, -2 sine theta plus 4. I've got a sine wave. Its frequency 1. There's no phase shift. All right, so that's good. So I know that this is going to trace out one cycle between 0 and 2 pi. So I'll put down my quarter marks. There we go. I've got a baseline vertical shift of 4. I've got an amplitude of 2, and it's going upside down. So instead of going middle, high, middle, low, middle, it's going to be upside down, right? So it's going to shift it and go like this, right? Or once again, just plug in the quarter marks and you'll get the correct value. So for example, if I look here, I would start here at the middle, and then at pi over 2, I would be at the low point, which would be 2 units away. Right, so this is at 4, and then this is at 2. Then I'd be back to the middle at 4, and then I'd be up at the high point, which would be 2 above the baseline, up at 6. And then back to the middle here. And so that's what it would look like. And once again, I can just always check, like plug in 0. Sine of 0 times -2 plus 4 gives me 4. Pi over 2. Sine of pi over 2 times -2 plus 4. You follow? Okay. Either way is fine. So now I want to see what this is looking like over here. So between 0 and pi over 2. So here's my thetas between 0 and pi over 2. The r value starts at 4 and comes into 2. So I'm going to start out here 1, 2, 3, 4. And as I rotate from 0 to pi over 2, the r is going to go from 4 and come into 2. So it's going to come in gradually, looking like that. And then from pi over 2 to pi, what happens? From pi over 2 to pi, it goes from 4, or 2 rather, back out to 4. So here's pi over 2 to pi. So it comes in and then it goes right back out to 4. So it goes right back out to 4. And then between pi and 3 pi over 2, it goes from 4 out to 6. So it's going out to 6. Uh-oh. I'm off the screen here. So let me just adjust. I apologize here. So we had, we started out at 4. We came into 2. So I'm just going to recreate this here like that. And then we went back out to 4. So like that. So that was from theta equals 0 to theta equals pi over 2 to theta equals pi. And now as I'm going to 3 pi's over 2, I'm coming out to 6. So down to there. All right. And then on the last leg of the journey, from 3 pi over 2 to 2 pi, I'm 6 heading back into 4. So that's going to get me back to where I started here. So that's theta is 2 pi. So this will bring me right back into there. Okay, so I get this sort of a shape. All right. Now once again, let's check this. Let's check this with Desmos. So I'm going to put in r equal 4 minus 2 sine of theta. And I'm going to check my theta. I went from 0 to 2 pi with the step of pi over 2. All right. So here we go. So from 0 to pi over 2, I went, there you go, from 4 into 2. And then from 2 back out to 4. And then from 4 down to 6 and 6 back. Okay. So Desmos is it's quick. It's a great way to help check that you're getting the right thing. And then, as you would do more, excuse me on that. So if you kept going, right, if you kept going with this sine wave, you would just be retracing what you already had. All right, so there's our graph. Let's take a look at number 2, r equals 2 plus 4 cosine theta. So once again, I like to start off over here in the r theta land. And let's write this as 4 cosine theta plus 2. So once again, we're given a standard cosine, frequency 1, no phase shift, vertical shift of 2, amplitude of 4, and this is a positive 4. So it's going to follow the traditional cosine pattern, high, middle, low, middle, high. So we'll go out here at 2. I have an amplitude of 4. So it starts off at the high point. Well, I guess we should do our quarter marks here. 2 pi, pi, 3 pi's over 2, pi's over 2. So it's going to start off at the high point, which would be 4 units above. So it's going to start up here at 6. Then it'll come down to the middle, which is 2. And then 2 units below, down to pi. It'll be 0. And then back to 2. Well, excuse me. I stand corrected. It's 4 units from the baseline. So 4 units from the baseline would get me down to negative 2. And then back to the baseline and back up to 6. Okay, so then I connect these dots in a pleasing pattern. Now, as we saw with that motivational example, when r goes from positive to negative, that means that we're going to be graphing. The graph is going to go through the origin and sort of be graphing in the opposite quadrant there. So it's important to know where this happens. So let's set r equal to 0. So that would give us that cosine of theta would be minus 2 over 4, or minus a half. So where's cosine minus a half? Well, either quadrant 2 or quadrant 3, that's going to happen at 2 pi's over 3 and 4 pi's over 3. So these are things we're going to have to watch out for here. 2 pi over 3 and 4 pi over 3. So we'll see how that actually figures in to our graph. Okay. So we start as normal. Here's theta equals 0. Theta equals pi over 2. From 0 to pi over 2, the curve starts at 6 units away and comes into 2 units. So 6, 1, 2, 3, 4, 5, 6. I guess we'll do that. And then it comes into 2. You can scale this however you want. I've just got this graph here for reference. So it's coming in like this, from 6 to 2. And now, from pi over 2 to 2 pi over 3, which would be in here, so there's theta is 2 pi's over 3, it goes from 2 to 0. That means it's coming into the origin here. So it's going to come into the origin at an angle of 2 pi over 3. So I'm going to dot that in because it's coming in at an angle of 2 pi over 3. And then from 2 pi over 3 to pi, we go from 0 to -2. So instead of graphing over here, we're graphing over here. So when we get to the -2 at the pi mark, we're back this way. All right, so it comes in at an angle of 2 pi over 3 through the origin, and now we're back 2 units over here because these are all negative values. Now between pi and 4 pi over 3, so I'm going to dot that down here, we go from -2 back to 0 again. All right, so in here, this would be pi to 4 pi over 3. Once again, the r values are negative. So instead of graphing in this part of the plane, we're graphing back over here. So we pick up where we left off, and now we're going to come in and cross through the origin at an angle following this 4 pi over 3. Between 4 pi over 3 and 3 pi over 2, we go from 0 back out to 2. So it comes through, goes back out to 2, and then from 3 pi over 2 to 2 pi, I guess I forgot to label 3 pi over 2, we go from 2 back out to 6, which connects up with where we left off. All right? All right, so I'm going to use Desmos to show what's happening here a little bit more closely. We can see it. But these, where the r goes from plus to minus, right? These are called the tangents at the pole, or the tangents at the origin. It tells you the angle through which the curve is going through the origin to connect to the other side. It's something you can verify when you get to calculus. But let's fire this up here and see what's happening here. So r equal 2 plus 4 cosine theta. And let's go 0 to 2 pi. Let's go in steps of pi's over 3. So we can kind of see this getting... well, actually, let's do pi over 6's. Right? So we do pi over 6's. That'll capture both the pi over 3 stuff and the pi over 2 stuff. Okay, so here we go. So there's 0. So 0 to pi over 6. Pi over 6 to 2 pi over 6 to 3 pi over 6. So this is our arc from 0 to pi over 2. That's our arc from 0 to pi over 2 that we had. That's the first arc there. All right. All right, now we're going beyond. So there we go. So now we're to pi over 2 pi over 3. So pi over 2 to 2 pi over 3, we start at 2, we're heading into 0. And now we pass through from 2 pi over 3 to pi. We're graphing now over here. So this is what I'm talking about with this idea of the tangent at the pole. This 2 pi over 3 right on the graph with the r theta graph, 2 pi over 3 is where the r went from positive to negative. Okay, so here's the r is positive, and then it follows that angle through the origin, right? R equals 0 is the origin. follows it through and graphs over here, okay? So instead of graphing over here, this would be theta equals 2 pi over 3. Shouldn't put it that way, because we're rotating counterclockwise here. The theta equals pi. Instead of graphing here, we've gone through, and we're graphing in the opposite part of the quadrant over here. So you just follow it through, right? And now from pi to 4 pi over 3, notice we're graphing here. So this is the other tangent at the pole, at the 4 pi over 3 mark. That's the other place. R was 0. And we are crossing from negative R values to positive R values. So from pi to 4 pi over 3, instead of graphing here, we're graphing in the opposite quadrant. And now we're going to pass back through the origin at the angle of 4 pi over 3. So there we go, until we get to 3 pi over 2. And now from 3 pi over 2 to 2 pi, we're graphing positive r's again. Whoops. Which gets us back to, at 2 pi, then we're back to 6. Okay. All right. So that's that example. All right. So this inner loop here, the inner loop that we had, so this inner loop here is what's being traced out with these negative r values. Okay, so this inner loop is traced between the 2 pi over 3 and the 4 pi over 3. So once again, Desmos is your friend with this. All right, it's going to take some time because you're having to think about graphing things instead of left and right, up and down, to out and rotate. And when you pass through the origin like that, you're going to the opposite end. So that's why Desmos will be a big help for you as you think about how these things are swept out. Asked to graph r equal 5 sine 2 theta. So what we'll do is go over here in r theta world. Let's see what's going on here. Instead of theta, we've got 2 theta. So our frequency is 2. That means the period is half what it normally is. So instead of running from 0 to 2 pi, this will run from 0 to pi. Oops. So put the quarter marks in. The amplitude is 5. All right, so we go to graph the sine function. The baseline is 0, and we're going to be moving 5 above and below. So 0, and then up to 5, back to 0, down to negative 5, back to 0. So there's our sine wave. And now we're going to try to, we notice it does dip below the axis here at, 0, pi over 2, and pi. So we're going to go ahead and sketch those in, because those will be the angles through which the curve crosses through the origin. So starting off here from 0 to pi over 4, the r goes from 0 to 5. So we're starting here right at the origin, and then by the time we get to pi over 4, we've gone out 5. So we'll go here 1, 2, 3, 4, 5. So we're going to be out to here. So we're going to come out this away. And then from pi over 4 to pi over 2, we're at 5. We're going to come back into the origin here like that. And then we're going to cross through, right? So r goes from positive to negative. Crossing through r equals 0 means we're going to be crossing through the origin here. And we're going in along the y-axis because that's the angle pi over 2. So instead of graphing over here in this quadrant, between pi over 2 and pi, we're going to be graphing in the opposite quadrant. So we're going to go ahead, come to 0, and now we're going to follow through. So here's 3 pi over 4. So from pi over 2 to 3 pi over 4, we're going from 0 to negative 5. So we're going from 0, the origin, following the pi over 2 line through to out to 5 again. So it's going to come out that way. And then from 3 pi over 4 to pi, we're going from negative 5 back to 0. It means we're going to be coming back in to here. And if we keep going, notice if we keep going, we would cross through positive again. All right, so if I went from pi to 5 pi over, or excuse me, pi to 5 pi over 4, we go from 0 up to 5 again, we're positive again. So I'd come through, carry through here, and end up back to here. You follow? So if I keep going, I'm actually going to be generating more of this graph. All right. So I'd have to go another cycle on the r theta graph, but I should be able to then trace out that. Now that's not the nicest looking thing ever, but let's check to see if Desmos bears this out. So we'll do r equal 5 sine 2 theta, and we'll let theta go from 0 to a, and we'll just adjust our slider, and we'll do our slider from 0 to 2 pi with the step of pi over 4, because that was the step that we had with our quarter marks. And let's see. So between 0 and pi over 4, there's our first arc. Second arc came back to the origin. We passed through along the y-axis, and then we graphed in quadrant 4. Then we kept going, crossed through, picked up the graph in quadrant 3, and then finished off with the graph in quadrant 2. All right. So once again, use Desmos here to help you know what's happening when. All right, our last example here, r squared equals 16 cosine 2 theta. What we really need to graph is r equals something. So if r squared is this, r would be plus or minus the square root of 16 cosine 2 theta, which would be plus or minus 4 square root cosine 2 theta. So here's how I like to think about this. Cosine 2 theta, that's going twice as fast as the regular cosine curve. So the period would be from 0 to 2 pi. So we have our quarter marks here. So instead of 0 to 2 pi, we're going 0 to pi, and we got our quarter marks. And what's going to happen with this curve is we're going to go between negative 4 and 4. And, you know, the regular cosine is going to look like this, okay? Regular cosine looks like this. Anytime I go below the axis, I'd be trying to take the square root of negative values. So that's just going to be undefined. So I'm really going to get a graph here between 0 and the first quarter mark here, which would be pi over 4. And then between 3 pi over 4 and pi. These are the only values I'm going to actually get a graph for. So the positive square root, cosine goes between negative 1 and 1. So the biggest this is going to be is 1. So the biggest that's going to be is 4. So the plus root, I guess I'll break it up into 2 here. So the positive 4 would come into here. And then this would all be undefined in here. We wouldn't get a graph for this area because between pi over 4 and 3 pi over 4, when I plug that in, that would correspond to angles between pi over 2 and 3 pi over 2, all of whose cosines are negative. So there would be this gap in the graph. Then I would pick up again from 3 pi over 4 to pi. Those would correspond to angles between 3 pi over 2 and 2 pi. I'd pick up and I'd get angles again. So that'd be the positive square root would be that. Now for the negative, then it would just be the reflection here. All right. So let's see what what this does for the graph. Because as we go from 0 to pi over 4, so here's the pi over 4 here. I go from 4 back in to the origin. So here we go. So 4 out, and I'm going to come back in. Right? It's very steep here, though. Okay, it's very steep, so it's going to come in like that. And then there's a gap, and then between 3 pi over 4 and pi, so then over here, I'm going from 0 back out to 4. So I'm going to do that. Okay, 0 to 4. So that would be that one. Here, with these negative values, right, instead of graphing here, I'd be graphing over here. So then I would be getting these values like that. And then likewise, I would be getting these values here like that. Okay. And so we got the lines here, the pi over 4 lines, which once again, I'm not graphing those very well, but there we go. We would get that kind of shape. So let's see what Desmos does with this. So if we try to, let's try to graph r squared equals 16 cosine 2 theta. It doesn't give us anything. So what we got to do is put the r in there, and we'll do a square root of this. So 4 square root cosine 2 theta. And then the negative. And we'll let theta go from 0 to a. And for us, we had a run from 0 to pi with the step of pi over 4. So let's see what happens here. See if I can get my colors to coordinate. So we have blue and green. So let's make that blue. And there's green already. Okay, so now we're good. So let's just go around here from 0 to pi over 4. We're tracing this part out from the positive root and this part out from the negative root. And then nothing in between until I get to 3 pi over 4, 3 pi over 4 to pi. We trace that out and that, and there it is. Okay? Now, it's worth noting that each of these curves here have special names attached to them. So there's curves that are called cardioids, limicons, roses, and lemniscates. And we have all those written out in the book. They're French categorizations of these things. The cardioid is called a cardioid, actually because it looks like a heart, so like a cardioid. It looks like a little heart. Okay, so things like that. Okay. The next example, we're asked to find the points of intersection of the graphs of the following polar equations. So if you remember back in like algebra class, if you were trying to find the intersection points between, say, y equals x squared and y equals x, so here's your y equals x squared, we'll put that in blue, and y equals x, we'll do that in red. Then all you had to do was set these equations equal to each other. X squared equals x. X squared minus x is 0. Factor. X equals 0. X equals 1. And then you'd plug those back into your formulas. And then we would get the intersection points 0, 0. And 1, 1. Okay? So you could set the y's equal to each other and solve for the x's. Plug the x's back in to get the y's, and we were good to go. Now the reason we were able to do this, even though you didn't think about it at the time, is because there's only one way to express a point in the xy plane. In other words, if we have points that are on both curves, those points have to satisfy this equation as well as this equation. They have to satisfy both equations. There's only one value of x and one value for y for each point. So these have to be the same, and therefore we can equate their equations. We didn't really think about it. Didn't think twice. So we can try that same approach here in polar, and then we'll see where we get into trouble with this. So we could start off number one here, saying, okay, well, I'll just equate the r's. So, 2 sine theta is 2 minus 2 sine theta. I'll add the 2 sine theta over. That'll give me 4 sine theta is 2. Sine theta is a half. Where's sine theta a half? Well, it could be in quadrant 1 or in quadrant 2. So I could pick a pi over 6, or I could pick a 5 pi over 6, plus any coterminal angle, right? But since we're looking for the intersection points, right, I only need one representation of each intersection point. So if I say take theta equals pi over 6, I can take r of pi over 6, and because I set these equations for r equal to each other, I should get the same regardless of what equation I plug it into. So if I plug it into here, 2 times the sine of pi over 6, sine of pi over 6 is a half, times 2 is 1. So this gives me 1 point of intersection, 1 comma pi over 6. And then likewise I plug in the 5 pi over 6. I get 1 as well. Right? So now let's just go ahead and do a quick check on Desmos. Now you could, with practice, you'll be able to sketch these pretty quickly. Like you'll be able to recognize what these things are. But for this example, we'll just put a quick sketch up on Desmos and then see if we get the correct number of points we should get. So we'll do r equal 2 sine of theta. Nice little circle there. And then r equal 2 minus 2 sine of theta. There it is. Whoops. And we can check points here. So the 1 point we had was 1 comma pi over 6. So if we look here, we've got, this is the circle radius 1. And sure enough, that's the pi over 6. So we can confirm that quickly. And then likewise over here, we're still on the circle of radius 1, but we can pick 5 pi over 6. So these are one representation each of each of the two intersection points. Okay? So setting the r's equal to each other in that example worked just fine. All right, let's take a look at the next one here. R equals 2 and r equals cosine of 3 cosine of theta. Once again, we can set these equal to each other. Set the r's equal to each other. Cosine of theta is 2/3. Now that's not one of the common angles we know, but 2/3 is a perfectly reasonable angle here. Or 2/3 is a perfectly reasonable cosine value. So I'm going to use the inverse cosine here, or arc cosine. So the quadrant 1, I can pick the arc cosine of 2/3. So that would be like my reference angle. And then for the quadrant 4, I can do a couple different things. I could just take the opposite value, or I could move it around. So I'll try this. You can tell the cat's upset about something. She's warning us about intersection points here. Okay, so let's try to, what would the points be then? So, well, you can plug this into either one of these equations. I should get r equals 2 out. Well, there's no theta to plug in there, so you're going to get 2 all the time. So the two intersection points we're getting are 2 comma arc cosine of 2/3 and 2 comma 2 pi minus the arc cosine of 2/3. These would be angles between 0 and 2 pi. We'll have to get some decimal approximations if we want to check, just to see how things shake down. But let's go ahead and graph that. So r equals 2. Nice little circle there. Center of 2 at the origin. And then we have 3 cosine theta. A little circle there. We see we have two intersection points. So notice both intersection points here are at 2. Now if we want to try to figure out, we're trying to approximate things here. The arc cosine of 2/3 as a decimal is 0.84. If you look, this is happening between pi over 4 and pi over 3. So as a decimal, pi over 4 is 0.78. As a decimal, pi over 3 is 1.0. So this certainly seems, this angle would certainly be between pi over 4 and pi over 3. So that tracks. Now if I take 2 pi minus this, I get 5 and some change. So looking down here, this angle looks between 5 pi over 3 and 7 pi over 4. So 7 pi over 4 and 5 pi over 3. So 5.44 and change is certainly between 5.2 and change and 5.49. Okay? So once again, we got both intersections. We got a representation for each of the intersection points. All right, let's take a look at this next example, r equals 3 and r equals 6 cosine 2 theta. So once again, we can start by setting the r's equal to each other. I'd get the cosine of 2 theta as a half. And so now I'm back to solving these basic equations. I've got the cosine of something as a half. So that something could be quadrant 1 or quadrant 4. So 2 theta could be pi over 3 plus any multiple of 2 pi. Or 2 theta could be 5 pi's over 3 plus any multiple of 2 pi. So theta then would be, well, I'd take half of all this, pi over 6 plus pi k, or 5 pi's over 6 plus pi k, where k once again is an integer. Okay. If I want to look between 0 and 2 pi, here I'd get pi over 6, and then I add pi. That'd get me down here to 7 pi over 6. Here I'm at 5 pi over 6 and 11 pi over 6. Okay. Now if I plug in each of these angles to either one of these, I should get the same r value. Here there's no thetas to plug in. The r value should always be 3. So I'm getting 4 intersection points. 3 comma pi over 6, 3 comma 7 pi over 6, 3 comma 5 pi over 6, and 3 comma 11 pi over 6. So I'm getting 4 points of intersection at each of the pi over 6's. All right. So that's what I would expect to see. 4 intersection points, radius 3, at all the pi over 6's. So let's fire up Desmos, do a quick check here. So we're looking at r equals 3, and r equals 6 cosine 2 theta. I'm going to zoom out a little bit so I can capture all the action. And you're instantly met with how many intersection points? 8. Which are the ones that we found? We found the ones at the pi over 6's. So there's the 3 comma pi over 6 and the 3 comma 7 pi over 6. So those were the first two we got. This is the 3 comma 5 pi over 6 and the 3 comma 11 pi over 6. So we're missing these, which appear to be coming at the pi over 3 angles. So the question is, well, what's going on there? And the answer is, remember, we can represent polar points with positive radii values or positive r values and negative r values. Okay. So if I look back here and I think about this, The equation r equals 3 can also be represented, that graph can also be represented by the equation r equals negative 3. Because remember, we can switch the r value and then just adjust the angle by theta. So remember, like if r and theta corresponds to an r prime and a theta prime, remember, if the r's are the exact same, the thetas would just be off by some multiple of 2 pi, or the r's could be the exact opposite, and the thetas would be off by some odd multiple of pi. All right. So r equals 3. If I replace r with its opposite, there's no thetas to replace. I would just be at r equals negative 3. So that's another way we can express points on that circle, which means that I could solve the equation. So now I got r equal negative 3, r equals 6 cosine 2 theta. Now I could solve the equation 6 cosine 2 theta is negative 3. So cosine 2 theta is negative 1/2. So now that means we'd be looking at quadrant 2 angles. So 2 theta would be 2 pi's over 3 plus any multiple of 2 pi, or 2 thetas would be 4 pi over 3 plus any multiple of 2 pi. Dividing by 2, multiplying by 1/2, here's where I'm picking up the pi over 3's. So here I would be getting, well, negative 3 pi over 3, negative 3 pi over 3 plus pi is 4 pi over 3, negative 3 2 pi over 3, negative 3 5 pi's over 3. So those are 4 new intersection points. Once again, it's a representation of the intersection points. There are infinitely many, and you can see that. So all of these r's here are negative. But we get to the pi over 3 angles. So negative 3 comma pi over 3 would get us to here. Negative 3 comma 4 pi over 3 would get us to here. So that would pick up those two. The negative 3 2 pi over 3 would get us to here. And then the 5 pi over 3 would get us to there. Okay? So you can hear that the cat's uncomfortable with this, because the algebraic method we used in college algebra still works as long as we remember that any given point in polar coordinates can have 2 different or infinitely many different representations. Okay? Here we've kind of got the most extreme example of intersection points. Let's set the r's equal to each other and see what we get. 3 sine theta over 2 is 3 cosine theta over 2. You might want to divide both sides by 3 cosine theta over 2 to get everything in terms of just tangent. And that's going to be fine, because if the cosine of theta over 2 would be 0 in this equation, that would force the sine of theta over 2 to be 0 as well. And sine and cosine can't be 0 at the same time. So we're perfectly fine dividing both sides here by the sine of, excuse me, the cosine rather, of theta over 2. So then I would get the tangent of theta over 2 equals 1. So where is tangent equal to 1? Well, that's at pi over 4 plus any multiple of pi. I multiply through by 2. I'm getting my thetas to be pi over 2 plus any multiple of 2 pi. etc. All right, so if I plug in the values here, let's see what I get. When theta is pi over 2, doesn't matter which one I plug these into. When I take pi over 2 divided by 2, I get pi over 4. 3 sine of pi over 4, that'd be 3 square root of 2 over 2. So one intersection point I'm getting from this is 3 root 2 over 2, comma, pi over 2. If I added a 2 pi or subtracted a 2 pi, so if I added a 2 pi or subtracted a 2 pi, let's say I'd have theta equal 5 pi over 2. Then r would be the sine of 5 pi over 4, 3 rather, sine, which would be minus 3 square root of 2 over 2. All right. However, if you think about where we'd have the point negative 3 root 2 over 2, 5 pi over 2. So where would this be? So we'd have pi over 2, 3 root 2 over 2 would be up here. Negative 3 pi root 2 over 2. We would start here and go around 5 pi over 2. So that would be down here. Okay. And so then we would just be bouncing back and forth between these 2 points. All right. So let's check that with Desmos here. R equal 3 sine theta over 2. We got that groovy looking graph. And we got 3 cosine theta over 2. And by golly, these graphs look identical. Okay, so what's happening here? What are we missing? Well, let's start with, say, r equal 3 sine of theta over 2. Okay, remember that for a point to be on the graph, r and theta, you have to satisfy this equation. But there are infinitely many representations. So, for example, we could replace r with minus r and theta with theta minus pi, right? Right? We could add or subtract any odd multiple of pi and get a representation of the point that corresponds to the same point on the plane. So let's do that. Let's replace r with its opposite. And let's replace theta with theta minus pi. And let's see where this gets us. That'd be minus r equals 3 sine of. And I'll do theta over 2 minus pi over 2. And I can go ahead and, well, you might recognize what this is. If not, we can just go ahead and hit this with the sum and difference formula. Sine of theta over 2 cosine of pi over 2 minus cosine of theta over 2 sine of pi over 2. So minus r equals 3 times. The cosine of pi over 2 is 0. The sine of pi over 2 is 1. So I get 3 times negative cosine theta over 2. And the negatives would cancel then, and I would get r equals 3 cosine theta over 2, which is the exact equation of the quote-unquote other curve. But it really is the same curve. All right. And so, once again, having infinitely many descriptions for a given point in the plane, it is a richness of the polar coordinate system. It lets us graph these curves as functions, r as a function of theta that normally wouldn't be, y as a function of x, or x as a function of y. But it also introduces this, I'm not going to call it a pathology, but this little wrinkle when you're looking for intersection points. So if you're trying to catch them all, right? Trying to Pokemon this whole thing, you want to sketch the graphs. All right, check to see if they intersect at the origin. All right, because that could be a point that you could miss. set the r's equal to each other. Keep the r's the same, but replace the thetas with coterminal angles. Or replace, flip the r in 1 and offset the theta by odd multiples of pi, and then set those expressions equal to each other. All right. So this is a lot of writing for what we actually saw happen in those examples. But this way you'll be guaranteed that you capture all of them. This example, we're asked to sketch the region in the xy plane described by the following sets. Okay. Now each of these examples are built up of things we've drawn previously. So we're going to use Desmos to sketch the curves, even though you should be able to sketch these curves by hand. So let's look here at the first one. R equals 0, that's the origin. R equals 5 sine 2 theta. And we want the points where the r is between 0 and this curve as theta runs from 0 to pi over 2. So we can actually go up here, 0 to pi over 2. That swept out the first leaf of that so-called rose. And so if I want the r bigger than or equal to 0 but less than or equal to 5 sine of 2 theta, that's just going to give me this region in here. It's the points where the r is between the origin and the curve. All right. So that's going to sweep that out there. Okay. The next one here, we're looking at r equals 3 and r equals 6 cosine 2 theta. So r equals 3 and r equals 6 cosine 2 theta. So we get that. I'm not quite sure why that's there. There we go. Okay. And so this is where we had those intersection points. We know one of the intersection points is up here at 3 comma pi over 6. That was one of them. And if I look at the region they want, they're only looking from 0 to pi over 6. So what they want is the angles of 0 to pi over 6. The r, you want r between 3 and the rows there, 6 cosine 2 theta. So here's the 0 to pi over 6 part. And so the region they're looking for here starts at 3 and once again goes out to that curve. So it would be this sort of part of the leaf. All right. So I guess I could restrict this here if I wanted to show that a little better. Whoops, sorry about that. So restrict this to pi over 6. There it is. And so we're looking for this region here. All right. R is between 3 and the curve for those angles theta. This is an interesting one. We've got the 2 plus the 4 cosine theta. Remember, this is the one that kind of had that dip and had that inner loop. I'm looking for where this is true for these angles theta. So notice we've got the curve here less than or equal to r, less than or equal to 0. So let's look here. Whoops. 2 plus 4 cosine theta. All right. Now that inner loop is what was formed between 2 pi over 3 and 4 pi over 3. Okay, so that makes that inner loop. But for each of these values of theta, r is a negative number. Okay, so r is negative number. So these are going to be negative numbers. So I'm still looking at the region of this curve between the origin and this curve, okay, because r is a negative at this point. So that would just be looking at this region here, would be looking at the inner loop of that curve. Okay. And last but not least, let's try to take a look at this one. R is between 0 and 2 sine theta, for theta between 0 and pi over 6, and then R is between 0 and 2 minus 2 sine theta for pi over 6 to pi over 2. So we might actually not have graphed these two. So you can do those, I guess, in the privacy of your own home. R equal 2 sine theta. It's your nice little circle there. And then R equals 2 minus 2 sine theta. That's one of these cardioids. So there it is. And you can check here that the intersection will be at, one of the intersection points is at pi over 6. All right. So let's see what they're trying to get at here. I want R between 0 and 2 sine theta for theta between 0 and pi over 6. So let's color code these with colors I can use for my pen. So we'll do red for this one, and we'll do blue for this one. Okay? So what would this represent here? So here's red. R is between 0 and 2 sine theta, 0 to pi over 6. So here's that pi over 6, which once again you can verify as an intersection point. Between 0 and pi over 6, I'm going from the origin out to the red curve. So that's going to give me this shaded area here. And now between pi over 6 and pi over 2, I'm switching over to the blue curve. All right. Now, once again, you can go through and verify that. So here's the pi over 6. That's the intersection point. Pi over 2, if I plug in pi over 2, I get 2 minus 2 sine of pi over 2. That's going to take me back to the origin. And so then I would be shading in that region between the origin and that. So this region here combined, I'm taking the union of these two. So I'm looking at this region together, and I'm breaking it up into the two parts, the part bounded by the red circle and the part bounded by the blue cardioid. Okay. So if you go on to calculus, in the second semester of calculus, usually you look at trying to calculate the exact value of the areas of these types of things. And so it's important that you have some background into understanding how to set these up as regions. So that'll do it for section 13.2.